Hey guys, this is Malinki. Welcome back to my channel, Voice of Malinki. Today we will talk about epistasis. And if you are new in my channel, please subscribe my channel. And if you like my video, please do like, comment and share my video. So, epistasis is nothing but a gene interaction where two genes interact with one another. So, it is an interaction between two genes. We can say that the action of one gene is dependent on the action of other gene. Suppose we have two genes, A and B. Now gene A is masking the function of gene B. The gene that is masking the activity of other gene is called epistatic gene, and the gene that is masked by the other gene is called hypostatic gene. Here, gene A is masking the function of gene B. So, A is epistatic and B is hypostatic gene. Suppose gene A makes a flower yellow and gene B makes a flower green. When gene A is present alone, the flower becomes yellow. When gene B is present alone, flower becomes green. When both gene A and B are present, flower becomes yellow. Because gene A is masking the functionality of gene B. There are 5 types of epistasis: dominant epistasis, recessive epistasis, double or duplicate dominant epistasis, double recessive epistasis, dominant inhibitory epistasis. 5 types of epistasis are there. We will discuss about them one by one. First one is dominant epistasis. In dominant epistasis, dominant allele of one gene suppresses both alleles of other gene. Both alleles means dominant and recessive. Suppose a plant has two genes, gene 1 and gene 2. Gene 1 has two alleles, capital A and small a. Capital A is dominant, small a is recessive. Similarly, gene 2 has two alleles, capital B and small b. Capital B is dominant, small b is recessive. Both gene 1 and gene 2 are responsible for flower color. Allele capital A masks the functionality of both capital B and small b alleles. Here, small a allele does not have any role because it is a recessive allele. Therefore, it is called as dominant epistasis because dominant allele of one gene, in this case that is capital A allele of gene 1, is masking the activity of other gene, in this case that is gene 2. Suppose a plant contains both gene 1 and gene 2. So both are there in a plant. Gene 1 gives a flower yellow color and gene 2 gives a flower blue color. If gene 1 is expressed alone, that means the genotype would be capital A or capital A small a. So gene 1 is expressed alone and gene 2 is not expressed. So when gene 2 is not expressed, the genotype would be small b. That is this case. This is the case. So flower will get yellow color. Now if gene 2 is expressed alone, that means the genotype would be capital B or capital B small b. And gene 1 is not expressed. So the genotype would be small a. So this is the case here. The flower will get blue color. If both genes are not expressed, that means small a, small b, where both gene 1 and gene 2 are not expressed, flower will be white color. Now what happens if both genes are expressed? So we'll check this cross. In the following cross, parent 1 has genotype capital A, small b. The flower is yellow because it contains allele capital A, that is suppressing allele small b. Parent 2 has genotype small a, capital B. The flower is blue because allele capital A is absent here. So allele capital B is not suppressed. When these two parents are crossed, their offspring in F1 generation will have genotype capital A, capital B, small b, and their color will be yellow because they have one capital A allele which is suppressing both capital B and small b alleles. If F1 generation offspring are self-crossed, there will be an interesting outcome in F2 generation. 12 flowers out of 16 are yellow. If one capital A allele is present, the flower will be yellow, no matter what are the other alleles. 3 flowers are blue. If allele capital A is absent and at least one capital B allele is present, the color will be blue because allele capital A is not present to suppress capital B allele. One flower is white because neither capital A nor capital B is present here. all alleles are recessive. Therefore, pigment is not formed. The phenotypic ratio of F2 generation is 12:3:1. Next is recessive epistasis. In recessive epistasis, recessive genotype of one gene suppresses both alleles of other gene. So, recessive genotype. Note that part, not recessive allele, but recessive genotype of one gene suppresses both dominant and recessive alleles of other gene. Suppose a plant has two genes, gene 1 and gene 2. Gene 1 has two alleles, capital A and small a. Capital A is dominant, small a is recessive. Similarly, gene 2 has two alleles, capital B, small b. Capital B is dominant, small b is recessive. Both genes are responsible for flower color. Flower color. Gene 2 is dependent on gene 1 here. To understand this better, we need to clearly understand this chemical reaction. At first, the flower does not have any color. Hence, it is white. Now, the allele capital A is acting on this flower and adding yellow pigment. When yellow pigment is already present, then only gene 2 can act on it and its allele capital B makes it blue. Therefore, gene 2 is dependent on gene 1. If allele capital A is not present, yellow color will not be formed and gene 2 will not be able to act. In the following cross, parent 1 has genotype capital A, small b, and it has yellow color because allele capital A is giving it yellow color and gene 2 contains two recessive alleles, hence they can't work and yellow to blue conversion is not possible. The second parent has genotype small a, capital B. It is white because allele capital A is absent here. Hence, it will not give the color yellow, and when yellow is not produced, allele capital B also can't give any color. When these two parents are crossed, their offspring in F1 generation will have genotype capital A, capital B, small b. They will be blue color because allele capital A produces yellow color and allele capital B makes it blue. If F1 generation offspring are self-crossed, there will be an interesting outcome in F2 generation. 9 are blue, 3 are yellow and 4 are white. All blue flowers have at least one capital A allele and one capital B allele. All yellow flowers have at least one capital A allele and two small b alleles. All white flowers have two small a alleles, no matter what alleles of gene 2 are present here. Therefore, we can understand that the recessive genotype of gene 1, that is small a, is suppressing both alleles capital B and small b of gene 2. Hence, it is called recessive epistasis. The phenotypic ratio of F2 generation is 9:3:4. Next is double or duplicate dominant epistasis. In double dominant or duplicate dominant epistasis, a dominant allele at either of the two genes can mask the expression of recessive alleles of both genes. Suppose a plant has two genes, gene 1 and gene 2. Gene 1 has two alleles, capital A and small a. Capital A is dominant, small a is recessive. Similarly, gene 2 has two alleles, capital B and small b. Capital B is dominant, small b is recessive. Dominant alleles capital A and capital B both will show their dominance. Neither of them will mask the functionality of other gene. Suppose we have a flower and gene 1 and gene 2 are responsible for the flower color blue. If dominant allele capital A or capital B is present or both are present, flower color is blue. If neither of them is present, flower becomes white. In the following cross, parent 1 has genotype capital A, small b, and it is blue because it has allele capital A which masks the expression of gene 2. Hence makes the flower blue. Second parent has genotype small a, capital B, and it is also blue because it has allele capital B which masks the expression of gene 1. Hence makes the flower blue. Therefore, it is called double or duplicate dominant epistasis because the dominant allele of a gene duplicates the same action of the dominant allele of a second gene and vice versa. When these two parents are crossed, their offspring in F1 generation will have genotype capital A, capital B, small b. They are also blue because they have both capital A and capital B alleles. If F1 generation offspring are self-crossed, there will be an interesting outcome in F2 generation. 15 flowers are blue because they all have at least one dominant allele, that is either capital A or capital B or both capital A and capital B. Only one of them is white because it does not have any dominant allele. The phenotypic ratio of F2 generation is 15:1. Next is double or duplicate recessive epistasis. In double recessive or duplicate recessive epistasis, recessive genotype of either of the two genes can mask the expression of other gene. In this case, both dominant alleles of two genes, when present together, only then they can complement each other. Suppose a plant has two genes, gene 1 and gene 2. Both are responsible for flower color. Gene 1 has two alleles, capital A and small a. Capital A is dominant, small a is recessive. Similarly, gene 2 has two alleles, capital B and small b. Capital B is dominant, small b is recessive. For example, we have a flower. Now, if both capital A and capital B alleles are present, the flower will be blue. Both capital A and capital B are present here. But if one gene does not possess any dominant allele, the flower color will be white, irrespective of the allele types of other gene. So, gene 1 and gene 2 are co-dependent on each other. In the following cross, parent 1 has genotype capital A, small b, and it is white. Because gene 2 has two recessive small b alleles, it masks the expression of gene 1. The other parent is small a, capital B. It is also white because it also has two recessive small a alleles and it masks the expression of gene 2. Therefore, it is called double or duplicate recessive epistasis because two recessive alleles of a gene duplicate the same action of the recessive alleles of a second gene and vice versa. When these two parents are crossed, their offspring in F1 generation will have genotype capital A, capital B, small b. They are blue because both capital A and capital B alleles are present here. If F1 generation offspring are self-crossed, there will be an interesting outcome in F2 generation. 9 flowers are blue and 7 flowers are white. All blue flowers have at least one capital A and one capital B alleles. All white flowers possess two recessive alleles of at least one gene like small a or small b, or two recessive alleles of both genes, that is small a, small b. The phenotypic ratio of F2 generation is 9:7. Next is dominant inhibitory epistasis. In the dominant inhibitory epistasis, a dominant allele of one gene masks the expression of both alleles, both dominant and recessive alleles of second gene. Suppose a plant has two genes, gene 1 and gene 2. Gene 1 has two alleles, capital A and small a. Capital A is dominant, small a is recessive. Similarly, gene 2 also has two alleles, capital B and small b. Capital A is dominant, small b is recessive. Dominant allele of gene 1, that is capital A, it is responsible for yellow flower color. Gene 2 does not produce any pigment. Gene 2 does not produce any pigment. What it does? So, it only masks the expression of gene 1. Hence, when gene 2 is expressed, allele capital B will suppress the functionality of gene 1. Therefore, the flower becomes white. Therefore, it is called dominant inhibitory epistasis because the dominant allele of a gene, in this case that is capital B allele of gene 2, it inhibits the expression of both dominant and recessive alleles of second gene, in this case that is gene 1. So, gene 2 is inhibiting the effect of gene 1 here. Now, capital A allele makes a flower yellow, like that. Now, gene 2 comes in action. If it has at least one capital B allele, it will destroy the functionality of gene 1 and will make it white. In the following cross, parent 1 has genotype capital A, small b and it is yellow. Because the allele capital A is making it yellow and it does not have capital B allele. So, nothing is present to mask the action of allele capital A. Another parent is small a, capital B. It is white because it does not have allele capital A. Therefore, yellow pigment could not be formed. When these two parents are crossed, their offspring in F1 generation will have genotype capital A, capital B, small b. They will be also white because although they have one capital A allele which makes the color yellow, they also have a capital B allele which will mask the action of allele capital A and make it white. If F1 generation offspring are self-crossed, there will be an interesting outcome in F2 generation. There will be 13 white and 3 yellow flowers. All white flowers have at least one capital B allele that masks the expression of allele capital A, or their gene 1 will have two recessive alleles small a, so that yellow color could not be formed here. All yellow flowers have two small b alleles and at least one capital A allele, so that the functionality of capital A allele could not be suppressed by capital B allele. The phenotypic ratio of F2 generation is 13:3.